Um, I'm Daniele Michilli. I'm a postdoc at MIT, and it's morning here in Boston. So I'm sorry, don't be alarmed if you hear some screaming. It's just my 1-year-old waking up. So I work in the field of fast radio burst. Let me remove these Zoom windows that are in the way. And today I decided to present a specific science case for fast radio burst, for one science case that I think is going to be an important application of fast radio burst, and I want to use this as an informative science case for what can be transient science with Argos. And I work with a telescope called CHIME in Canada. Regrettably, I forgot to put a picture on my slides, but thanks to the advantage of online presentation, I just Google it. So this is CHIME, which is, it's in Canada, and you can see it's formed by these 4 cylinders with, on the focal lines, 1,000 antennas.
Daniele, sorry, your slides are not advancing on the Zoom.
Oh, I'm sorry.
I think you're sharing the wrong window.
Sorry about that. Let me share it again. Share. Do you see CHIME now?
Yep.
Oh, okay. Sorry about that. Yeah, I was saying this telescope in Canada that some of you may know is formed by these 4 half cylinders, and on top of the focal lines, I hope you can also see my cursor, but on top there are 1,000 antennas that always look up and search for radio transients and 21 centimeter and pulsars and a lot of cool signs. And I just want to mention that could be relevant to this venue that we are also working on an improvement, an advancement for CHIME, which is called CHORD. And this is a pretty bad rendering, but gives you the idea. Basically, the idea is pretty simple. There are these 500 antennas on a square in a field. And the idea is pretty similar to what I believe is Argos concept, but this is highly optimized for transients, and this is one of the reasons why this is on a grid. And as you can see, it will be next to CHIME, and it also has 2 out-trigger stations at thousands of kilometers for VLBI, as Jason was mentioning. But as I said, this is optimized for transient signs, and so we only have 2 stations, so it's not for imaging. Anyway, I just think that looking at some current and past experiences is very informative for Argos. And so going back to my slides, which I hope you can see right. Since the discovery of fast radio burst, the science that we can do with them has been divided into broad fields. The first one is understanding their mysterious origin, and the second is using them as tools to study the universe. My primary interest is in the second, in the second thing, at least for this talk. And you can see the most famous example on this picture of how we can use fast radio burst as cosmological probes when the authors have used them to characterize the intergalactic medium, so the medium that is in between galaxies. I guess Jason already told you everything about fast radio burst, dispersion measure, and propagation effects. But what is important for this plot, for example, is that we plot on the vertical axis the amount of free electrons between us and the source, which is parameterized by the dispersion measure, and the distance of the source on the horizontal axis. And the color points are the fast radio burst, and the line is not a fit, but is a result of simulations that that include the so-called missing variants. So the free electrons that come from cosmological simulations that are not observed in galaxies, and so we believe that they are indeed in the intergalactic medium, and this was confirmed by this beautiful plot. This is just to show you one possible application of fast radio burst, and this is probably the lowest hanging fruit, and so is where the community is at the moment spending most of the resources. So using the propagation effects, and in particular this dispersion measure on the signal of fast radio burst, to study the media which is between us and the source. There are other examples. For example, a very cool one I think is constraining the mass of photons with fast radio burst, and some exotic applications like this. And one that I want to talk about today is the detection and use of gravitationally lensed fast radio burst. I will start with an introduction about the science that we can do with gravitationally lensed fast radio burst, and how we can use them. And just to give a very quick introduction, because I don't think this audience needs much, but in gravitational lensing is, of course, the bending of the light from a background source by a massive lens along the line of sight back to the observer. And for example, in this picture on the right, we can see an AGN, so a supermassive accreting black hole, which is at high redshift, and a galaxy in between, which is visible in the middle, and this galaxy forms these 4 images on the sky. This is called strong lensing, and it happens when the mass is a galaxy or even a galaxy cluster. In this talk, we are all interested in galaxies, and it's important to notice that the separation between the images is about an arcsecond, and and if the source varies, for example, its flux increases, you will see this increase at different times in the different images, and the typical time separation between the delay is 10 days. And this is called time delay cosmography, and the delay depends on the parameters of the lens and on the parameters of the universe. And so if we model the lens, we can measure parameters of the universe, and in particular the Hubble constant H. Thanks to this method, we've measured the Hubble constant down to a precision of 2.5%, which is, in my opinion, incredible. But there are discussions about unaccounted errors, because this requires a model of the lens, which is difficult to obtain, and there could be some some issues with the model, which result in higher errors on the Hubble constant. And the second problem is that we want to reach a precision of 1%, and going from 2.5 to 1 is very hard. So the community has been looking for other possible sources to use. Traditionally, we've used these AGNs, which are numerous and bright, but the brightness is also a problem because it outshines the background galaxy, making it difficult to model. And their light curve has a slow variability, and which means that measuring a delay is only possible for a fraction of the AGNs, and they're in general difficult to model. These light curves vary randomly, and supernovae have been our recent addition. They have a predictable light curve. They are transients, which means that we can go back to the source, observe it when the supernova had faded, and model and obtain observations to model the lens more precisely. And the fact that some standard candles, of course, help with distances, but the light curve is still slow varying, and multiple observations are necessary, since when the supernova is on, it outshines the host galaxy as well. Other sources that have been investigated are, for example, gamma ray burst, but these are rare and also difficult to localize. So there is no confirmed lens gamma ray burst yet. This is when fast radio burst come in the picture. They have a lot of advantages for this kind of study, and they, I think, are even better than what a time delay cosmographer could dream of. First of all, they are very common. There are thousands that reach Earth every day. We just need to find and detect them. They only emit in radio, or at least they've only been detected in radio, and so they don't outshine the host galaxy. That also they don't need to be included in the lens modeling. The duration is of course of an order of milliseconds, and so this allows us unprecedented precise measurements of the delay. As Jason said, some repeat, and so with the repeaters we can even study the evolution of the properties over time, which is both helpful to place further constraints on the lens, but also some exotic applications, like for example measuring the variation of the delay over time due to the expansion of the universe, and so add new constraint on the Hubble constant. In addition, there are other advantages with fast radio bursts that weren't really thought in the past. For example, they are polarized and they can be used to study the magnetic fields of the lens, and they are coherent, meaning that if we correlate the signal of a fast radio burst with itself, we can reach delays down to nanoseconds, which is incredible. And so the only thing that is needed is to detect them. And this is, of course, where Argos comes in the picture. Before discussing of Argos, there are another two phenomena that I want to quickly mention. The first one is microlensing, which is exactly like strong lensing, but at much smaller scales. So the lens, instead of being a whole galaxy, is a single compact object, such as a star. And usually, if you have a star that crosses your line of sight, you detect microlensing, as in the top picture. You see the flux of the sources that goes up for a period of time, typically tens of days, and you can model this curve accurately and obtain the mass of the object, for example. But in case of strong lensing, each image, as you can see in the bottom panel, is formed by a lens, which is a galaxy, and in turn, in a galaxy, there are a large number of stars and compact objects. And so, if we could zoom in one of these images, you will see that is formed by a myriad of micro images, each of which is formed by the ensemble of the stars in the galaxy. And for AGNs, this is a problem, because when you observe them, the stars in the galaxy move near your line of sight, and so the ensemble of stars results in a flicker of the light from the AGN. And for example, you can see these two images at the top that were taken, I think, 2 years apart, and the two bottom images, the flux is basically reversed due to this flickering for the microlensing effect. With fast radio burst, we have the possibility of resolving single stars in another galaxy for the first time. So while with AGN this is impossible, because the images themselves are separated by micro arc seconds on the sky, so there is no telescope that can distinguish them. So we see all these micro images that are there as a single blob. There's no way we can separate them. And in time, they're separated by microseconds. And so with AGN, again, this just look like a flickering image that flickers over months. We cannot reach microsecond. There are projects to go down to a millisecond. There was a very cool talk here a couple of days ago, so I suggest to check that out if you're interested. But with fast radio burst, for the first time, by going down to delays of microseconds, we can actually start to distinguish the images. And here on the bottom is a plot of the magnification, so basically the flux of the source as a function of the delay, and you can see this swarm of images that arrive in an exponential fashion. But the first images that are the brightest can be isolated with fast radio burst, and so we can measure the mass of stars in other galaxies, which is, I think, extremely cool by itself, but it also enables us a lot of science, such as measuring the mass to luminosity ratio for a galaxy for the first time. And I'll go quick here, but as I said before, the propagation effects can be studied with fast radio burst, but usually the problem is that a propagation effect is the sum of all the intervening media, so it's impossible to distinguish which contribution comes, for example, from the AGM versus the host galaxy, and we need models or approximations that have very large uncertainties. But with a lens fast radio burst, if we take the difference between two images, we can basically remove all the contribution, but of the lens. And so with a sample of, I'd say 10 strongly lensed fast radio bursts, we can actually have create a 3D map of the interstellar medium in another galaxy, in an elliptical galaxy for the first time, which is another very nice application. So let's discuss about how we can detect this lens fast radio burst. At first, I have created some simulations that account for the population, for the characteristics of the population of fast radio burst and the lenses and the telescopes, and all of this to simulate detection rates for future instruments. And also, to measure a delay, we want to measure to detect 2 images separated by 10 days. And this is extremely difficult because, of course, radio telescopes only observe a tiny fraction of the sky. And it is only possible if we know that a fast radio burst is lensed. So I think that there are 3 ways we can do that. Looking in the literature, the first is looking at galaxies that we know are lensed. Euclid, in a few years, will release a catalog of about 150,000 galaxy lenses. And so if we localize the fast radio burst from one of these galaxies, we can follow it up with other interferometers around the world and detect the second image. And this should provide about 1 fast radio burst every 5 years with chord. So here, in my simulation, I used the characteristics of the chord instrument, which are pretty similar to what we expect from Argos, and so the numbers should be similar for Argos. The easiest thing to do, though, will be to just look at the North Pole for 1 year, and we detect 5 lens fast radio bursts, and we do all of these cool signs, and the case is closed. We can move on. We would recognize that these are lens fast radio bursts and not repeaters because they are separated by about an arc second on the sky, and we don't need any follow-up with other instruments. The third possible method that exists is looking for signatures of microlensing in the signal of fast radio burst. And when microlensing is seen in a fast radio burst, and there are multiple images, we know that it crossed a galaxy on its path, so there are high chances that it's lensed, and so we can use optical data to look in this direction, see if there is a lens, and follow that up again with other interferometers. Yeah, I don't want to go too deep in this scenario, but just a quick summary of what I said. We can detect the first image of a lens fast radio burst with a sensitive telescope such as Argos, and then there are observing strategies to detect a second image. We measure the delay with unprecedented precision. We obtain deep optical images to model the host and the lens, and we measure the Hubble constant and other cosmological parameters. We can study the microlensing between delays of nanoseconds to milliseconds and detect single compact objects, resolve single stars in other galaxies, and measure their masses. And this is also a way to constrain, for example, models of dark matter Finally, the signal of fast radio bursts can be used to estimate the properties of the lens, in particular the interstellar medium and its magnetic fields. And finally, these are some an instrument designed for this goal will look like. It's a fast radio burst discovery machine. So you'll need to search a large parameter space because you want to have a large field of view to discover many of these, a large range of dispersion measures, different time widths, possibly optimized for different spectral indexes of the fast radio burst. But fortunately, many of these specialized searching algorithms exist, so we don't need to reinvent the wheel. We can just collaborate with people that have written these tools. Localization for all fast radio burst signs is essential, as Jason has remarked. So I'm not going to spend much time here, but for this specific science case, we don't need millisecond precision, as Jason was mentioning, but 100 millisecond will be enough. So with a few antennas outside the core of the telescope, that's doable. Again, for all fast radio burst signs, and a lesson we've learned, it's very important to store voltage data from the antennas, better if from single antennas. And this is, for example, in this case, this is essential to measure microlensing, but it's important for a lot of applications. The only thing, of course, is that processing a store voltage data, especially if it's from the antennas instead of being formed, is expensive. So this should carefully be planned for, and it will require a large amount of storage. And any estimate you have about the storage, multiply at least for a factor of 4, because we filled it up pretty quickly with time. Lastly, it would be great to point to the North Celestial Pole for this scientific case for long periods of time. I know that this is not going to happen because other science cases will is detrimental to other science cases, but just wanted to point it out, so in a few years I can come back and tell you I told you so. It would be great. But jokes apart, this is the summary of my talk, and I hope this science case has been informative has been a good example for an application that we can use Argos for in the next future. Thank you.
It didn't come through. So thank you very much. That was very interesting. So we can see if there are any questions in the room or online. So I have a very, very naive question. So I didn't quite get where this requirement for the 0.1 arc-second localization come from. I mean, what do you lose if it's not that good, and what do you gain if it's better than that? I mean, why it has to be in that range?
Absolutely. For this scientific case, there are two requirements. One is that we want to separate the different images of the fast radio burst on the sky, and two, we need to know the position together with the delay to measure the Hubble constant. But in general, more in general, for any science case regarding fast radio burst, we want to localize them to know what is their host galaxy. And to do this for high redshift fast radio burst, we need this sort of precision, because otherwise there is an ambiguity of which one is the host galaxy. And knowing the host galaxies is essential to know the distance of the source. So we should, for fast radio burst science, I think this is really the goal. And doing better than this will mean knowing where within the galaxy we are. So it will bring advantages to know, for example, what is the source of fast radio burst, or or some science case that require this.
Okay, thanks. So Jason, you can unmute yourself.
Yeah, so just following up on that, Daniele, isn't it the case that I mean, with higher precision on the astrometry, can't you actually image the separate images of the burst as they are lensed, and hence get better constraints on the mass of the lens, etc.? Doesn't that help you reduce covariances between the cosmological parameters and the lens model?
Yeah, that's exactly true. I think that this 0.1 arc second is the bare minimum, but if we get millisecond precision, of course, this is better for measuring the parameters, since as I said, we need the position together with the delay for this task.
Yeah, and in the context of like Olaf Hoeknitz's paper, I mean, you'd be measuring the positions and evolving delays between bursts, right? I mean, you would actually be, I mean, you would be seeing the universe expand at some level, right?
Yeah, indeed. Indeed, this is the thing, that the delay measurement is so precise that you see it evolving as the universe expands, which is I think is incredible, but also it will remove the necessity to model the lens, and so measure the Hubble constant only through the delays.
So then that's the way to go, I guess.
One way to go, at least.
Yes. Okay. So Daniele, thank you very much for your very, very exciting talk.